Hello. Welcome to the Smart Mobile Solution Newsflash Special on Simulation. I'm Emre and I'm here with my colleague Nadia today.
Hello, welcome to the today's simulation newsflash. We have prepared the following topics for you. So first we will see what is simulation and why do we need it. Afterwards, we will see what are the current challenges in the field on RDE and simulation. And then we will see how we can tackle these challenges and revolutionize the whole process. At the end, we will have a look at our outlook for next year. So Emre, why do you think we need simulation and why are we talking about that today? So where do we need simulation in the whole development process and what is road digitalization?
Okay, well, if you look at the process again over the V cycles, we see that the development starts on the concept level and it goes for components on the testbed environment, but still most of the development is concentrated on the road testing. And while doing the road testing, the OEMs or suppliers are tackling with the complexity of the road testing, which means the different environment conditions, different road gradients, traffic conditions. Of course, the variety of the vehicles should not be forgotten. And of course, the driving styles is also an influential factor. This reduces the repeatability of the test on the street. Today, the customers are tackling with this complexity by front-loading this activity to different testing environments, starting from the complete vehicle test up to powertrain test, component test, field test, or even to the simulation in the office. But to be able to be reproducible and representative as the real world test, one important element is to bring the road conditions in a digital way into simulation environments. So we are talking about the virtual road conditions. And to be able to efficient and accurate enough, this process needs to be fast, accurate, and to be able to go to the market in a timely wise, it should be also very quick. Therefore, we concentrated in AVL to develop solutions that facilitate this process.
That's really interesting. But what do we mean when we talk about virtual RDX testing? What is RDX?
Yeah, nowadays everyone is talking about real driving emissions. So emissions are today by law needs to be also measured in the street. But it's not only about emission. When we talk about real driving, it's not about only emission, but also fuel consumption, durability, drivability, or certain function validation. And these topics are not only interested, this is what we call basically the RDX testing. So the X stands for different development activities.
And why is the real world driving and front loading so important?
Because it's not only about the emissions and the powertrain development. Today we see in the market that the complexity of RDX is addressed in the emission powertrain development, engine calibration with the stringent CO2 targets is an important topic. But we see the same pattern in the development activities of electric vehicle, for example, from different complexity of the electric vehicle and different variety also requires a reproducible, accurate testing in the street. Then, of course, the ADAS. In the ADAS, the OEMs are subjected to different uncertainty and then the number of numerous scenario road conditions. We can extend this topic to the other development tasks in powertrain development, vehicle development, chassis development. So all these activities are always subjected to the complexity of the real driving testing. If you look at only the emission challenges, again, by law, there are certain limitations in terms of the aggressiveness of the driver or in terms of road conditions. So, for instance, if you look at the emission results comparing different driving styles, it has a very impactful effect on the resulting emissions. And also the environment conditions, even the wind effect may result in different emission results. And when you go on the street, you never know what type of traffic you will be subjected to. And the altitude is also a very important factor that influences the fuel consumption, the ambient conditions that the engine is subjected. This results again the variety of results in the emission.
Right. And on top of that, we shouldn't forget the specific RDE challenges as for example the RDE trip requirements that have to be fulfilled. So the driver has to drive a specific amount of time in urban, rural, or motorway, and also the driver effect, how aggressive and how peaceful the driver should be driving. As you mentioned before, traffic conditions, limits, speed limits, and vehicle constraints should also be considered as challenges that we have to tackle for the RDE testing. So, do you know how AVL is approaching these challenges?
Well, AVL has recently developed a methodology in order to front load this. Yeah, here due to all these different conditions, there is obviously a reduced reproducibility on the road testing. We can call this a kind of randomness, basically, and this results with a different variety of results in terms of emission, fuel consumption, or different KPIs. To be able to deal with it, AVL developed the following methodology. We take first the representative cycles to the different testbed environments or into the office, where the reproducibility, repeatability is much higher due to the, let's say, controlled conditions. Once we ensure the reproducibility, then we can address the different conditions by means of simulation. For example, we can tune the aggressiveness of the driver. We can address different vehicle conditions, vehicle mass, for instance. We can vary in a controlled way the altitude conditions, ambient conditions. Plus, in the laboratory environment, or so to say in the testbed environment, we have much more precise measurement techniques. I'm not saying that in vehicle testing we don't have enough solutions or precise solutions, but they are meant to be done only for street testing. But the laboratory measurement techniques are different and provide a more accurate result.
Nice. But another question I have is how currently the car manufacturers are instrumenting their vehicles for collecting this road measurement data?
Well, this is a very good question. Actually, there are different techniques depending on the interested subject. Let's take, for example, the powertrain domain. In the powertrain domain, the instrumentation is mainly focusing on the emission measurements with PEM systems. Plus, there's a limited, let's say, sensing device to measure the position of the vehicle, let's say GPS, and the rest of the measurements are relying on the onboard sensors in the vehicle, because at the end of the day, the developers are trying to develop software which is based on the onboard sensory system. But if you look at the vehicle domain, the instrumentation is slightly different. There where the OEMs are focusing more precise instrumentation, more precise vehicle positioning system to be able to sense the sleep conditions, lateral, longitudinal sleep conditions. Therefore, they are equipping the vehicle with a very precise measurement techniques. Additionally, most of the time the road conditions, surface conditions needs to be also understood to be able to tune the control systems, body control systems. And there's a third domain. Let's say this is this new ADAS autonomous driving domain, where the vehicle positioning is important, but additionally the environmental perception is also a topic. Therefore, the amount of data the customers or the OEMs are dealing is a different size, let's say. But I must say that today we will focus more on the powertrain domain, and the solutions we will present today will be around powertrain applications. Nadia, where do you think these cycles can be utilized?
This can be utilized at the chassis dyno, or we can also have them at the powertrain testbed, at the engine testbed, at the hill system, or even at the office environment with simulation tools.
Okay. We are also providing office simulation tools, which are like a CruiseM, VSM, but we are also open to bring other third-party office simulation tools to this environment.
Yes, but let's have a look also on the challenges in terms of the road digitalization, as you mentioned in the beginning. So here, what we can see, one of the challenges we have here is the noise that can occur while measurement. So how can we make sure to filter out and avoid this noise and get the accurate measurements? On top of that, we also have to deal with the GPS accuracy to make sure that we have always the right position of the vehicle. When the vehicle is stopped due to stop signs or traffic lights, we have to make sure that there we don't generate any noise and we have the exact position of the vehicle. And also when measuring in a low sampling rate, it can occur that we don't get the exact position of the driving of the vehicle. As you can see here, we also have to deal with some loss of data while measurement, or even when we are inside a tunnel and the GPS signal has been lost, we have to make sure that we also get the data from there. But of course, there are also other challenges in the road digitalization that we can add here.
Yes, let me explain the specific phenomenon, what we call time-distance domain synchronization. Typically, when we measure the position of the vehicle, we use a GPS sensor. And this gives up to certain level of accuracy, certain positioning of the vehicle. Yeah? On the other hand, we are using other sensors to measure the vehicle velocity, or even we can fuse these measurements with the GPS sensor positioning to come to a correct vehicle velocity. Let's assume that the vehicle is driven on a straight road and then goes into hill condition. And during this, let's say, driving conditions, the vehicle loses its speed on the hill condition and again gain the speed again at the end of the hill. This is just a simulation of the real phenomenon. This is how the vehicle is driven really in the vehicle. But of course, the vehicle speed we measure is not that smooth. There is also noise in it. Yeah. So we measure like in the graph a noisy signal, which is shown at here with the dash line, and then we see the noise factor on it. How do we deal with the cleaning of this noise? Yeah, the first approach is applied to a filter, but as we all know that the filter will bring a certain delay in the signal. And let's simulate with the delay signal what's happening. So the car is approaching at the constant speed to the hill, and during the hill, right now we have a different speed velocity condition. And eventually, when the driver is let's say finishing the hill condition, then the speed velocity is still not as it should be. So this is a very well phenomenon that we call, let's say, the unsynchronized time and distance domain signals. And this results with the, let's say, mismatch of the road gradient and velocity. If we use, for the sake of cleaning data, this, let's say, unsynchronized velocity profile, then we can come up with the different load conditions at the testbed environment. Additionally, the emission and fuel consumptions are measured according to the legislation by gram per kilometer. Therefore, the distance covered by velocity should match the distance measured with the GPS signal. In case of RD signals, this may result of hundreds of meters unsynchronized data. So this is also a very well-known phenomenon. But if we extrapolate this condition to the curvatures, there is also another thing. Yeah. So here we see a vehicle approaching to a curve with 60 kph, and after the curve, let's say the vehicle accelerates afterwards to 100 km. Due to the same phenomenon, applying a certain filters either on GPS signals or onto the velocity, then the velocity will not match anymore with the road geometry, and the vehicle may enter to the curvature with a higher speed. And eventually, as we see in the animation, then the vehicle can lose this stability or leave the road. This may result in the simulation environment. Hopefully, this doesn't create any issue, but at the end, the simulated will stop or the testing will end. So then the user needs to clean this mismatch and goes for the continue for the simulation or testing. And this can result with the, let's say, high manual effort to bring all the velocity time-based data to the geometry of the data. Yeah.
So the question is, how can we tackle all these challenges? And the answer is simple: road to RIC with one click, which means for the different use case and workflows that we have, there is also, we will present a solution about this. So the three workflows that we have identified are the following. So the first occasion is that we want to reproduce an RDX road measurement, so we have the measurement data there available. The second workflow is that we do not have measurement data, but we want to create own synthetic RDX cycles and different scenarios. And the third occasion is when we want to combine the first two. So when we are doing measurement in the street and we want to extend these measurements with new conditions and RDX cycles and new scenario creations. So if we have a look on the first workflow, so when we have real measurements from the street, how we can bring them to the simulation. So for that, we have a tool where we can easily convert the real measurement data to simulation data. So we get as an input format data from a PEM system where we have done the measurements in the street. And by using our tool, Smart Mobile Solution Road Converter, we can convert this measurement to ready test cycles for chassis or engine test beds. We can see here that we support different output formats for Puma, IGEM, Isaac, and so on. And in that way, you can really easily filter, clean the data, and then export them to simulation-ready data. So if you want to see more specifically how does this work?
Yeah, let's have a look to the details. Yeah, as you mentioned that there is a direct importing functionality, so there is already not a need for converting the data format from PEMS measurement or AVR move systems to the SMS road converter. There is also some additional benefits. For example, as mentioned at the beginning of the presentation, then even in the powertrain there might be a different logging system that collects the data from the onboard sensors plus the emission measurement. And there is also automatic synchronization, data synchronization that fits the data in the time and the distance domain. So we can support a multiple logging file format already in Road Converter, which can be automatically synchronized afterwards. Once the data is imported and once the road is visualized in the tool, then we can start tuning the data. As we mentioned several challenges of the data cleaning. Yeah? The tool is automatically finding the issues at the data, for example, the loss of signals, the automatically detected noise level. Additionally, we are directly connected to the digital map services. This helps us to also, in terms of filtering, to clean the data, especially when the data doesn't match really the road position. Then we can snap the information back to the correct road position. The user can interact with the data if it wanted. It can he or she can extract a certain portion of the data, stitching together different portions of the data, and as mentioned, there are some automatic filtering thing. It's a very common thing that at the onboard measurement system, sometimes there are some missing information. For example, the gear position is always not either not detected or not measured, or there are some delays in the gear positioning. We are also dealing with fixing this missing or flawed data of gear selection points. The next step then is to prepare the data for simulation and testbed application. Here the user can add additional conditions such as the artificial wind or additional virtual road gradient can be added by considering the curvature loads or wind loads. And specifically for chassis dyno application, especially with the BACS measurement, the selection of the phases are also important, and the tool is automatically allowing the user to select where the BACS, emission BACS can be selected at the different phase. For example, on urban section of the road, the first BAC can be selected, and then the highway section, another BAC can be selected. Yeah, by considering the limited or by considering the parameterization of the CVS tunnel. Once the preparation of the data is ready, then we can export the data into different formats for directly to be utilized at the testbed systems. As we know, AVL PUM automation system is using a certain specific format for test definitions, test case definition, and this format we are using, exporting is can directly be imported into the automation system. But we shouldn't forget the pure simulation. Therefore, the tool is able to generate specific or general format, which can also be utilized in various different simulation environments.
Yes, so let's see also how the solution looks like in case of the road digitalization. So here we see in the example before that the measurement noise has been cancelled, so we are able with Roll Converger to correct the noise that has been generated and clean it up. Also, in case of the stopping points, we can reduce the noise during these stopping points. Also, road and time data has been synchronized and corrected, and the signal loss and data flows are compensated. So in case of data loss here, we are able to estimate and retrieve the data. So if we have a look now on the second workflow, where we don't have real measurement data, let's say we are really early in the vehicle development, or we just want to generate our own scenarios and synthetic RDX cycles for simulate worst case conditions, how here the solution looks like. So for this case, we have the cycle generator, AVL cycle generator, where you can simulate and create your own RDE cycles. So how to do this? You can generate an RDE valid route that you want to drive in the simulation. Here you can select the vehicle type that you want to use. And the driver type, so if the driver should drive normal, aggressive, or peacefully. Also, you can generate your own traffic conditions and traffic signs, so you can place inside the trip where should be traffic or where should be less traffic. And based on these configurations, the tool will calculate an RDE cycle, which can then be used in the simulation and testbed.
That looks great, yeah. Now we can also look into the details how this route calculation, route search is done. As you all know that there is a certain specific conditions when it comes to RDE, specific regulations, how the route should look like. The tool, by using direct access to the digital maps in a certain specifically selected area, can find multiple route alternatives according to the different country legislations, for instance, for Euro 6 or for Indian RDE legislations. Besides the RDE specific route selection criteria, the tool is also able to, or the user can define specific KPIs in terms of route length and altitude conditions to modify or to customize the search criteria. In this case, different trip share conditions of urban, rural, or highway can be selected. And it's not also limited to automatic search criteria. There is always the possibility to add specific roads by interacting with the manual waypoint additions. This is the part where the route is selected. Once the route is selected, then the route can be utilized in the vehicle as a navigation information, or it can be also utilized in the cycle generator to create a realistic synthetic cycles. In this case, there are also different options. For instance, the cycles can be designed depending on the specific VA pulse or RPA criteria. VA pulse and basically the RPA, which stands for relative positive accelerations, are the limits or KPIs which are given by the RDE legislation to quantify the aggressiveness of the cycle. And the user can define at the beginning of the process in which target VA pulse or RPA level the cycle should be created. This is an important capability, and the user can define upfront the aggressiveness of the cycle, or can define the different worst case conditions. Besides that, we can also utilize the physical phenomenon like the traffic information or the road attributes to create a cycle. In this case, the RDE legislation criteria will be resulted out of the cycle creation process. In this case, the driver types can be also utilized. But the tool is not only designed to make a synthetic cycle creation and then utilize at the testbed. Directly in the tool, the user can create multiple cycles in order to identify the worst case condition.
Correct. And this brings us to the last point, where in case where we want to combine the real road measurements with the extension of them and generate of new scenarios. So here with the cycle generator, we can import also the real measurement. So we don't need always to generate the route in the tool. We can also use an existing route that we have driven outside in the street. So we can import the measurements, and we can add different scenarios that are not included in our measurement in order to extend the real driving conditions and create different scenarios in order to validate them against the calibration robustness. So we can perform sensitivity analysis, we can find worst cases conditions and analyze them further, or a critical condition that we want to do more details in the simulation. So in this case, we can use the tool for the combination of the first two methods that we have seen.
To sum up, we have presented today a toolchain that accelerates the road digitalization. And the important factors is first the compatibility, so that the road measurements or with PAM system or different data logging systems can directly be utilized without processing further the data. Usability is also in part important factor, because thanks to intuitive graphical user interface and thanks to designed workflow scheme, the user is directly oriented by the workflow of these three cases and can generate the cycles accordingly. And not to mention about the unique features, AVL has developed certain mathematical algorithms and also use certain software technologies to facilitate the fast data processing and to address all the challenges we have mentioned at the beginning in terms of fixing the data, smoothing the data, utilize the digital map sources, and fuse all this information in order to create a smooth data digital virtual road model. And finally, the benefits. All this process without having a tool in the background always takes a lot of manual effort and consumes a lot of resources in the development process. And we try to facilitate this by bringing high efficiency in the data digitalization, road digitalization. Eventually, the quality of the road data is a very important factor that influences the reproducibility at the in front loading of the RDX development.
Thank you, Emre. So you really summed up what we talked today, and we presented the solutions we have in order to tackle the current challenges that we have talked. But we don't stop here. We continuously develop the tools and also bring in new solutions. So what is next? We want to consider also online and statistical traffic in our tools, and also to extend the digital map coverage so that we can also deal with local map providers like in Japan and other countries. And one also important aspect is to consider also cycle creations for electric vehicles and plug-in hybrid vehicles, where we can there create synthetic tests based on the calculation range of the battery. And also we extend our applications in order to consider the heavy-duty applications and vehicles. So today we talked about the challenges and also the solutions, and we gave you a brief overview about what we have and how we can solve the issues. Please write us your feedback. We would really appreciate your feedback or questions you have to today's webinar under these email addresses that you see here, or if you need any more information that you would like to know from us. And feel free to download also a free demo version of our software under avl.com/sms. So there you can we can provide a demo version for some months where you can see the tool and try it out and see if it fits also to your workflow.
Thank you for listening. Stay healthy, stay tuned.
Thank you so much. Stay safe, but stay connected. Bye.